Hello dear students. As a part of enhanced learning for the benefit of students, I am coming up with a lecture series on microelectronics. In these lecture series, the students will be explained about various aspects of MOSFETs and its usages. Basically, I am going to deal with these contents which is shown on the screen, wherein all the contents are bifurcated in terms of different modules. And definitely I'm going to put it on the web. You can glance through the contents, and the textbook that I'm going to refer for this lecture series is Microelectronics Circuits, Etc. and Casey Smith, 6th edition, Oxford University Press. So keep listening to these lecture series, and maybe we can learn a bit in an enhanced manner. So to begin with, I here assume that the students are aware of fundamental concepts of MOSFETs, like its construction, drain current equations, conditions for saturation region and triode region, and different biasing techniques. Hence, I'm not starting my lecture series with a very fundamental concept of MOSFET. Rather, I'm starting my lecture series from the large signal analysis or large signal DC analysis. So this is lecture number 1, large signal analysis or DC analysis, which we are going to start.
DC analysis, or basically large signal analysis for my MOSFET, by considering certain example wherein I'm going to consider VDD of 10 volts, and let's consider VT of 0.5 volts. Kn dash W by L is equal to 1 milliampere per volt square, and we have already figured out or we have already plotted the DC load line by using this particular MOSFET amplifier circuit, and by applying KVL we try to obtain this particular equation, and through this equation we already plotted the DC load line. Now that we'll try to figure out what is the importance of the DC load line when it comes to input and output characteristics, or basically the transfer characteristics, which means we know that for an proper amplification to happen, the MOSFET has to be biased in saturation region, and to ensure the MOSFET to be in saturation region, we need to abide by certain conditions. That is, the current has to be flowing constant and the MOSFET has to be in the saturation region. Now, using that particular load line graph, which was something like this, the VDS versus ID graph, for different values of VGS we have plotted the load line, and this will be VDD by RD, and we have seen this will be our Q point. Now what is this graph is going to give us in terms of its input and output values? For example, for any small incremental value of the input voltage, how is that this particular MOSFET is going to respond to for that particular small changes in the input voltages, or basically small DC voltages. So when we do a thorough transfer characteristics analysis, we'll come to know that what should be the range of this particular DC voltage that I need to be maintaining throughout the entire operation of this MOSFET, wherein it can work as an amplifier. So the basic agenda is this. So in which region this has to be biased? Of course we know that it has to be biased in saturation region. Now basically when I start giving the input, in which all region this MOSFET tries to move through, like whether it will be in saturation region always when I start increasing this VGS, or will it be in saturation then comes to linear then comes to cutoff, or will it be in linear then comes to saturation and then comes to cutoff? I don't know as of now. So let's try to figure out this by increasing this VGS voltage, that is DC voltage, and trying to plot a transfer characteristics. Now in order to do that, so as I told, I'm going to plot an output voltage for a different change in the input voltage. Now this is the output voltage equation. Now in order to get the output voltage, I should be knowing what is VDD, that I have assumed it as 10 volt. I should also know what is the value of RD. So let RD be also equal to 1 kilo ohm, and I should be knowing what is ID. Now in order to obtain ID, I need to calculate that ID. So let us calculate ID for different value of VGS. So for VGS equal to, let's consider 1.5 volt. Considering the equation of ID, let us assume, let's consider ID equation as the drain current equation in saturation region. So this is my equation. Now for this value of VGS of 1.5 volt, so what will be my ID value? So if I can substitute this over here, so I'll do one calculation. So this will be 1, I have already taken, so this will be 1.5 minus 0.5 whole square. This will be 0.5. So for VGS equal to 1.5 volt, I'm going to get VD equal to 0.5. Now similarly for VGS equal to 2 volt, ID will be, again if I substitute VGS equal to 2 volt in this equation, maybe you can see 2 minus 0.5 is 1.5 whole square, and divide by 1.25 whole square will be 2.25. So for VGS equal to 2 volt, if I substitute over here 2 minus 0.5, 1.5 square, this is 1 by 2. So if I calculate that, ID value will be 1.125 milliampere. Similarly for VGS equal to 2.5, let's calculate what is ID. So if I do that calculation, it will be 2 milliampere. Kindly verify the calculations. If I go for VGS equal to 3 volts, my ID value will be 3.125 milliampere. For VGS equal to 3.5 volt, ID will be 4.5 milliampere. For VGS equal to 4 volt, ID will be 6. I have already calculated it, so making it easy for you to understand. And for VGS equal to 4.5, my ID will be 8 milliampere. So these are the values of my current for different value of VGS. Now I can use these values of ID and the value of this RD and all these values of ID in this particular equation to obtain my output voltage. Now let's do that and let's try to calculate what will be my output voltage for different values of ID and RD and the given VDD. So let's do that. So for different values of VGS, I have already obtained ID. So let's replace this value of ID and RD equal to 1 kilo ohm in this particular equation and try to obtain VD, which is nothing but my output voltage. So the equation will be as simple, since VDD is 10 minus my ID is 1.125 for the first case. Let's do it once again. So VD is 10 minus 1.125 milli and RD is 1k. Kilo and milli it will cancel out, and my equation will be a very simple equation, 10 minus 1.125, which will be 8.875. So this is my VD for this current, or this is my output voltage for this input voltage. So let's try to rewrite the things in a very simple manner. VD is equal to 8.875 volt. For VGS equal to 2 volt, then current will be 1.125 milliampere. Now if I can keep on doing all these VD value for different sets of current, so for my second condition it will be straightforward. VD will be 8 volt for VGS equal to 2.5 and ID is equal to 2 milliampere. So similarly for the third case, if I can do it for all the cases, let me do it for all the cases and let me write it over here. So if I keep on doing the calculation, I'm going to VD equal to 8 volts for ID equal to 2 milliampere, because I can simply substitute this ID equation, ID values over here. Now if I move further, if I calculate for ID equal to 3.125, my VD will be 6.875. So similarly my VD value will be, I'm getting different values for different value VGS. Now one interesting thing you can see over here, as and when my VGS, that is my input DC voltage, increases, my output voltage is decreasing. So this is what I'm going to plot it, which I'm going to call it as a transfer characteristics, and I'm going to correlate this transfer characteristics with respect to the VI characteristics of my MOSFET, which we already plotted. So let's plot the transfer characteristics. So if we can mark all the points of my different values of input. Now here input is nothing but my VGS, what I have already taken, and for that I have already calculated different voltages, that is output voltages. Firstly I calculated for this value of VGS what is the current, and I utilized that current values in the output voltage equation, and then figured out what is my output voltage. And if I can plot all the points, and once I join all the points, this is what I'm going to get the graph. So this is the graph which we call it as a transfer characteristics of MOSFET, which correlate the VI characteristics of my MOSFET. And the thing what I can interpret from this graph is, so let's plot the graph of ID versus VD for different value of VGS. So let's try to plot so this is my ID for different value of VGS. So here for different value of VGS, when I say these are the different value of VGS that I already obtained over here, for these different value of VGS I'm going to plot the earlier graph where I did my, or I figured out the load line or quiescent point load line analysis. Yeah. So this was for VGS equal to 2, 2.5, 3, 3.5, and we also figured out the load line. Yeah. Now what this graph explains. So fine. So from this transfer characteristics, we are going to try to correlate the things of my ID, VD, that is VI characteristics of my MOSFET. So basically, so this is the transfer characteristics we already plotted for different value of input, that is for different value of VGS. How is my MOSFET going to respond in terms of its output? So if I can plot the, I already plotted it here, the MOSFET's VI characteristics. Now this is for different value of VGS. I have drawn different curves on my load line which we already plotted, and we're trying to interpret. So from the previous graph the two inputs or the two values that I can consider here is for a different value of VGS, what was your VDS, right? Now how this graph and the previous transfer characteristics are correlated, or how they are helpful in thorough analysis of MOSFET, let's try to figure out. Now you can see here for VGS equal to 2 volt, we obtained here so for different values of for VGS equal to 2 volt, this should be over here 8.8, this is 8, this is 6.8, this is 5.5, this is 3.8, this is 2. Yeah, so for VGS equal to 2 we obtained an VDS of 8.8. For VGS equal to 2.5 we obtained VDS of 8. For VGS of 3 volts we obtained VDS of 6.8, and henceforth we obtain all the values. I just vertically I have dropped down all the values over here. Now let's try to get back to the condition which clearly bifurcates whether the MOSFET is in saturation or is in triode region. So basically our condition was VDS if it is greater than or equal to VGS minus VT. If this is an NMOS, this will be in saturation region. Now let's try to verify all the values. Now as we know, this particular flat surface indicates the MOSFET is in saturation region, and this particular curve indicates the MOSFET is in linear region. Now let's try to figure out. So for VGS equal to 2 volt, what is the VDS? It is 8.8. For VGS equal to 2 volt, my VDS is 8.8 and threshold was whether this 8.8 whether it is greater than this particular voltage. Yes, hence this particular MOSFET for a value of VGS generating an output voltage of 8.8 volts with so and so current is in saturation region. If I can go ahead, let's consider 2.5 VGS. So if I can substitute over here for 2.5 volt, what was my VDS? It was 8, and the condition still holds good. Now this condition holds good till the point I reach, let's consider 4. So for VGS equal to 4 volt, VT is 0.5 volt, and for 4 volt of VGS, what was my VDS? I obtained a 3.8. Now let's check whether this condition holds good. Whether 3.8 is greater than 4 minus 0.5, that is 3.8 is of course greater than 3.5, which means this is the value of VGS where my MOSFET will either be continuing in the saturation, or if slight variation happens to this particular VGS, it may be even pushed down to triode region. So this particular portion is my deciding factor, which tells whether my MOSFET is entirely pushed into saturation region or it is whether the MOSFET is still in linear region. Let's consider the example of for VGS equal to 4.5. Now for VGS equal to 4.5, VT is 0.5. What was your VDS generated for 4.5 volts? So for 4.5 volt, as we can clearly see here, my VDS generated was 2 volt. Now this 2 volt, definitely it is less than this condition, so which means for a VGS of 4.5 volt, my MOSFET will be in triode region. Of course, these graphs are not that perfect to indicate the device is in triode region, but from the mathematical calculation we can always figure out that after 4 volts of input voltage, my MOSFET is not going to satisfy the condition of VDS greater than or equal to VGS minus VT, which also means that less than 4 volts of VGS, my MOSFET will be in saturation region. More than 4 volts of my VGS, my MOSFET will be pushed into triode region. And that's where we define MOSFET's operating conditions, indicating if at all my MOSFET has to be in saturation region, I can choose any one value of VGS which ensures the device is in saturation region, which means I can choose a value of VGS equal to 4 volt, VGS equal to 3.5, VGS equal to 3, VGS equal to 2.5, or VGS equal to 2 volts. Any of these value of VGS is corresponding VDS satisfies the condition of saturation region, and it ensures the device will be in saturation region always. And this makes the foundation for amplification that we are going to perform by pushing the MOSFET in the saturation region. So the same thing can be seen over here, the graph which we have done. As you can see here, these are few points where my, like for example, I told the MOSFET has to be, or basically these still here, more than 2 volt, less than 4 volt. So this is the region where I can say that the MOSFET will be in the saturation region. So to ensure a proper swing, to ensure that output voltage is not clipped off, we usually consider the MOSFET, the value of VGS and the corresponding value of VDS to be in the center of this particular transfer characteristics, which happens to be for VGS of 3.5 volts. So the same thing is seen over here. So which means basically my Q point lies over here. That is my operating point. So to summarize, so if I can operate my MOSFET with 3.5 volts of VGS and generate 5.5 volts of VDS with an respective current for 5.5 volts of VDS, I can also see here the current, coming back to this, so for VGS of 3.5 volt generating a VDS of 5.5 volts and maintaining a current of 4.5 milliampere ensures my MOSFET is pushed into saturation region always, and my device is not going to fluctuate or deviate from these particular values. Thereby I can ensure that the MOSFET will be in saturation always. Since I am dealing with all the large signal, that is DC voltages, and I have nullified all my AC signals, and this sort of analysis whatever we did to interpret this particular graph and this load line or the transfer characteristics, it is basically your DC analysis or DC load line analysis or large signal analysis. So this is how we can get the or we can interpret the transfer characteristics and its corresponding VI characteristics to ensure the device or the MOSFET will be pushed into saturation region always. So let me summarize the things once again for you. So basically we started with this particular circuit, and we obtained the output voltage equation by applying KVL at the output node, and this is my output voltage equation. And using this output voltage equation, I try to substitute different values of VDS and ID. For example, if I substitute VDS equal to 0, my ID value will be equal to VDD by RD, which is over here, this point, for VDS equal to 0. For VDS equal to 0, and for ID equal to 0 on this curve, if I substitute ID equal to 0, my VDS value will be equal to VDD. So basically I joined these 2 points and I obtained a load line. Now initially I chose this point as Q point, and later we figured out how I arrived at this particular Q point. So what we did, once I drawn this load line on different curves of VDS versus ID for various values of VGS, I have many graphs, and then I got a load line. Now from this load line, I say that my device has to be always biased with respect to this particular value of VDS, generating this much amount of current using this much value of VGS, then only my MOSFET is bound to be in saturation region and my amplification will be distortion free. And in order to justify all this point, we did some small mathematical calculation wherein we try to consider this equation which we applied as a part of KVL, and then for different values of VGS we try to find out what are the respective currents, and like that we did for different value of VGS what was my current, that we did in this equation. Now that we did in the equation of my ID. So for different value of ID I obtained different VGS. Now using for different value of VGS I obtained a different current values, and using these currents I am going to resubstitute the current values over here, and I am going to obtain what are my different output voltages. So basically for VGS1 what is my current, and for that current what is my output voltage. Similarly for VGS2 what was my current, and for that current what is my output voltage. Similarly for VGS3 what was my current, and for that current what is my output voltage. So basically once we did all these things, we plotted that in the form of table, and we obtained something like this. For VGS equal to 2 volt I obtained a current of 1.125, and for this current I obtained output voltage of 8.875. So like that we did for different values of VGS, different IDs, and we obtained different VD, and then we plotted something called as we obtained something called as transfer characteristics, wherein we did the plot of V in versus V out, that is for different value of input what was my output. So once we plotted, we obtained a graph something like this, and we try to correlate this transfer characteristics graph with respect to VI graph or VI characteristics graph of my MOSFET, which was over here. Now again the same graph is being repeated over here. So for different value of VGS I plotted the graph of VDS versus ID, and then for various value of VGS there is the generation of different VDS that also has been marked. Now these values are being obtained through the load line analysis in the previous through the previous equation. Now substituting these VGS and VDS value in the saturation condition, we tried to figure out what are the different gate to source voltages that can be considered to ensure proper amplification, and that we figured out that for different values of VGS right from 2 volt till 4 volt the condition VDS greater than or equal to VGS minus VT is satisfied, but where then when my input voltage, that is VGS, is at 4.5 volt, so when I substitute VGS equal to 4.5 volt, the condition didn't satisfy. This condition became the condition for triode, which means my MOSFET entered into triode. So basically we can summarize that for VGS equal to 2 volt till 4 volt my MOSFET will be in saturation region, so which means I can consider any of these voltages as my biasing voltages, and I can ensure that my device is in saturation region. Of course 4 volt is pretty dangerous because 4 volt happens to fall at the border of the edge of the saturation and triode region. As you can see here, if I can put 4 volt over here, the condition is 3.8 volt greater than 3.5, which means it is on the edge. So let's not consider this voltage. So to be on safer side, the Q point is always considered at the mid of this particular graph, so which is basically for 3.5 volt. So if I can consider this particular thing, my Q point lies over here, which is for 3.5 volt, generating an output voltage of this, and for 3.5 volt of input voltage, what was my current? My current was 4.5 milliampere. So this was a summary of this entire exercise that we did, and this clearly demonstrates the behavior of MOSFET to ensure proper amplification, the load line analysis, the VI characteristics analysis, and how we can say that the MOSFET can amplify the signals, ensuring distortion less, or basically without having any distortion, how my MOSFET can amplify the signal. So this is it from this lecture. We'll continue with the next lecture in the subsequent classes. Thank you.